Hello and welcome to this hardware design and development course by Mindmajix. Every groundbreaking piece of technology, from the smartphone in your pocket to the servers powering the global internet, starts with a single layer of copper and a vision. But how do you go from a concept on a paper to a physical working device? In this course, we are pulling back the curtain on the world of electronics engineering. We are not just talking about the theory, we are talking about the actual hardware lifecycle. In this course, we will cover electronics fundamentals, circuit design and analysis, embedded systems, hardware testing, debugging, and validation. Today, companies in IoT, automotive, robotics, and EVs are actively hiring skilled hardware engineers. According to LinkedIn and Naukri, hardware engineers typically start at around 4 to 8 lakh rupees per annum in India and can earn more with experience. If you want to learn hardware design and development course with certification, then check out our course where we will cover latest industry curriculum, hands-on projects, labs, mock interviews, and more. Before moving ahead, I want you guys to like, share, and subscribe to our channel so you never miss any tutorials and courses from us. So let's get started with our HDD course.
A topics prerequisite topic, really, some of the basics of electronics, both digital and analog electronics. Going to look at is basically for digital caption is interfaces are important for digital design. As for the analog design, the noise management is important. Just to say. So here are the prerequisites. Definitions, the gates, flip-flops, counters, timers, common digital electronics elements that we want to look at. And also on the analog side, we look at PAC, timers, multivibrators. We start with what is called triple five timer on the analog side. A triple five timer can be used as a multivibrator. Basically, this is the configuration. This can be used in something called monostable multivibrator. What is a monostable multivibrator? Just to remind us, essentially, if at the input here, if you give it a trigger pulse like this, the monostable multivibrator will hold that pulse for that long duration. A minimum time of t, which is basically computed by T1 equal 1.1 to R1C. Here is R1 and C1. Basically, when we press it, it's basically comparing this voltage, the voltage that charges across R1, C1 from V to C, it would charge when we trigger this, and then it would charge to, capacitor voltage will charge this way exponentially. And till it reaches to this two-third VCC, it will look at it, then the comparator kicks in, not when the pulse goes up. So this is nothing but a monostable vibrator, typically used in research circuits. We'll look at it. When we apply a reset of the microcontroller to stay for minimum duration. So that minimum duration. This is something that we have done in the basic electronics. So this hopefully this will help us serve as a revisiting it. And then the same triple five timer can be used as a multi-vibrator, where it would basically generate a square wave with T1 and T2 time durations. So this is where the battery VCC is connected, and this is R1 and R2 and capacitor C1 and C1 are connected this way. It generates basically at the output. Here is the output. Here it generates a square wave. Just to demonstrate, it's connected in LED, which will go on and off. Right? That's a multivibrator. That if you remember, essentially it will be self-oscillating and then generates a square wave. So that's how multivibrator. Some of the mixed signal components, that is the ADCs, are something we're going to discuss more about them in detail. But here is something we can actually look at more. So Mouser is a component. Let's go to the website, see how we actually can, or from DGT or Element 14. These are the computer vendors that I usually order. Yeah, here is a more involved block diagram analysis. We have section on ADC where we will discuss more on ADC. But just it takes these analog input channels and they are multiplexed within the chip, and takes the analog and converts into digital and read through a standard digital, filter them to 12-bit ADC on, or let's say four channel, and by selecting the chip filters out, and then this is how you select the copy. We come to the master side more often again. So that's basically an ADC. ADC is essentially what it does is converts an analog voltage. Similarly, a DAC is something that converts to analog conversion. So typically in ADCs basically come with multiple ADC. Single ADC is very uncommon. And what is digital to analog conversion is? It takes the analog voltage 0 to 5.0 volts or 0 to 10.4 volts, whatever the range of the analog conversion takes that and converts into digital data. So 0.000 is converted into 000, it's an 8-bit ADC. And this is converted to 255. So 0 to 255, every value in between is converted into ADC. So this is ADC, to analog conversion.
So these are the standard binary conversions for these 3.75. So how are you actually converting these analog to these digital values? Is there any method? These are the standard ones.
Just linearly. That means 5.0 is equivalent to 255. This is 255. So 3.75 what's the 5.0 you 255 you divide by 5.0 times 3.75 will give you an integer value. That integer value. Similarly, half of this, that is basically 128. So divided by 5.0 divided by 2.5, it's 2. So this 255 divided by 2 is half of that is 128 roughly. This is how the ADC conversion happens. So, and next time when we need to convert the digital data from 128 to analog, but again this is something that depends on the ADC range. Wherever the ADC is the range. So it can be from 0 to 10.0 also. So 255 might become 10.0 and then 128 becomes 5. It all depends on how we configure the ADC. When we look at the ADCs, there is something called the reference voltage based on that. When we get to that point, so this is the ADC conversion. And here it is, there is then another common thing that we use is voltage divider in the circuits. It's basically this divides the voltage into R1 and R2. So the voltage across R2 using the Ohm's law is basically V into R2 by R2, voltage divider. Then we move on to more of analog components, the op-amp. Op-amp is essentially offers a gain to input voltage and gives an output of gain, right, as we all know. So there are two kind of gain amplifiers, inverting op-amp and non-inverting. The inverting op-amp, we know the voltage basically becomes negative. That means V out by gain is based on this divide or resistor divide ratio, RF by minus of RF by R. This is an inverting amplifier. The voltage is basically being fed to the negative terminal here. So the output is negative. This is a non-inverting amplifier where the voltage is fed to a positive terminal. The negative terminal through the resistor is grounded. Here the gain is 1 plus RF by RA. This ratio 1 plus RF by RA. The gain here. So these are the two configurations that we can use op-amp in inverting and op-amp. And then op-amp can also be used as low-pass band processors and these kind of things. So we're looking at a couple of other configurations, low-pass filter and high-pass filter. What is a low-pass filter? It essentially passes every frequency below a cutoff frequency. It passes it, and every frequency above the cutoff frequency it does not pass. Right? Of course, it would have a characteristic. It won't immediately stop. If the cutoff frequency is let's say 120 hertz, and if you pass a 125 hertz, it will attenuate it, not completely stop it. But if you pass 1000 hertz, it will completely attenuate. Right? We know that there would be a frequency response to this to the filter. So that's something again. Just to revisit, these are things that we already know from basic electronics, right? Nothing. We're not adding any value, trying to remember and have what we have done. So here is a low pass filter. So yeah, the cutoff frequency is. I didn't give the formula here. You can actually look it up. But here the cutoff frequency is basically is derived from the resistor value and the capacitor. So this is a low pass filter configuration, and here is a high pass filter configuration. In the high pass filter, basically the capacitor is on the side and the resistor is there. That means what happens is during the transition, the capacitor acts during a square wave or whenever transition happens. The capacitor acts as a shock, and then the inductor acts as open. So if we pass a high pass frequency, high frequency, it acts as a short, so the input would come as is, and then it gets amped. With a low pass, this acts as a DC. If we are applying with DC, it acts open. The capacitor is open, so the signal won't come in, and then so the high frequency, the low frequency won't take care of the DC won't. That's how we can tell whether it's high pass filter. But then, yeah, in case of high pass frequency, here is the formula is given here. Amplitude is R2 by R1. This R2 by R1. The frequency is 1 to pi into RC. R is basically R1, R1C. This is the RC is the time constant that's given. So this is the analog. Digital component. Now we move to the digital. I think in the analog set we cover most of the analog basic components on which everything builds up. If we basically the ADC that we looked at is basically is a integration of many analog components and digital components together. But we don't really put them on the PCB board separately, independently. There are integrated VLSI chips that are already available that we use. The modern design is we don't try not to use discrete as much. We don't use discrete design and do the discrete design. So here is a NAND gate that consists of 4 NAND gates, 2 input NAND gates, and this is from the LS74 series. There are so many of these LS74 series ICs that one can look at it. 74000 is quad 2 input NAND gate. 7401 is quad 2 NAND input NAND gate. Similarly, quad 2 input NOR gate and quad 2 input NAND gate is one more. Is again an AND gate. And here is an X inverter gate. 7404. 6 inputs. This list is actually given on, if you search for list of 7400 series integrated circuits on Wikipedia, the entire list you can get it. Even
why is it called 7400 LS7400? Is there any
don't know. No, when it started, I think they have given a series number, 74 series number. So it stayed when they started in 1960s, I think 1960s or 1950s. They chose that series, and then so it stayed with it. When the first semiconductor, everybody uses that as a standard, and they don't change it. Given that any semiconductor. But after that, the semiconductor part standardization is left to the manufacturers, not to a common consortium. So now all the ADCs, these are basically numbered by the manufacturers, so there is no standard. But on the gates, so they have standard gates, because there were many manufacturers that were supplying to the defense, and all of them were basically using the standard number initially. So the digital components, flip-flops, basically the flip-flop inner construction is, as we know, is basically the 2 NAND gates connected, and this is specifically a D-type where there is a clock, and the signal is the data D is passed in here, and its invert is passed to the other side of the circuit. So D-type flip-flop. So output here is Q, and this is the Q bar, Q naught, opposite of Q naught is. So what this essentially does is whatever data is put in here, this it comes here at the clock edge. It basically takes that value, and it is basically nothing but a memory cell. Remembers that value even if the data is removed. It maintains this value here due to this feedback loop that is there. When this is something that we have studied already in detail, a deep technical. Of course, if you look at in any of the microcontroller design, we don't use at all deep for whatever reason. But then again, sometimes once in a while you may have to use. We work with basically integrated IT. But just use an idea of what if we are looking at a reset circuit and say there is a flip-flop inside it, we know what it means, right? When we look at that. And here is the truth table for the flip-flop. Here is the symbol of the flip-flop. Truth table is 0, 0. Then whatever Q in the clock is 0 and clock is 1. D is 0 and D is 1. When the clock becomes 1, that's when basically the data actually gets to the output 0 and then 1. When the clock is 0, the output doesn't get affected. It stays whatever Q is and it stays the same. It doesn't change. Whereas when clock is 1, the 0 is passed on to the Q and 1 is passed on to the opposite stays at the Q bar. So this is basically what it is at the level that basically triggers a level triggered.
So you said we don't actually use D flip flops as such, right? So what do we use if we want to use D flip flop? I didn't get that.
So
we
what
want
we
to
mean
use.
We will never get in a microcontroller board kind of design. We generally never get a reason to use a DP. It's not that
Necessary.
it's generally not necessary. But rarely it may be needed, then we will use it. Whatever reason we have to use, we'll use it. It's not that it's forbidden to use, but then rarely we get a chance to.
Okay.
Yeah. But it might be embedded within the reset circuit IC. We're using a reset IC. And then the description when we are reading the data sheet, it's a reset IC, there is a kickback, then we know about it. So then digital components, other things are basically multiplexer, decoder, PCB to 7-segment decoder. Let's look at the data sheets of the. Here is the Texas Instruments TI website. There is a multiplexer and a decoder. The 74 series LS138, and then BCD 7-segment decoder, SN74247 IC. Let's look at it. Yeah, here's of course the NAND IC. Before I go to the 74 series LS74. Okay, NAND flash. So we look at D74 LS74. This is the D-type flip-flop. So the flip-flop is coming in basically, two flip-flops basically, essentially. Clear and then the clock, clear to clear it to back to the reset. It has more number of inputs than the actual clock. So they would obviously give us a, here is the function table of the truth table. Clear and clear. For clear, when clear is applied, high is applied, it basically Q clear to high. This is the table of that. And here is the functional diagram of that. Clear and clock. Three blinks are also set here, just to set the pre and clear. Clear the flip-flop as well as set a preset value into the truth table. So again, that's like the read and write into the, not exactly read and write, but similar to that. So instead of a simple D flip-flop, you got something like this. Of course, if we want exact D flip-flop, it may be there also. We have to just set it. And here is the data sheet. Okay, indeed. and the typical the frequency at which it can operate. It can only operate at maximum of 25 megahertz. Okay, there is no maximum limit here. So minimum is frequency 15. That's interesting. Why here doesn't have a max, but typically it can be used at 25 megahertz. That's something. Okay. And here is how the package basically would look like, and the package dimensions. Here is the package of a dual flat pack. We look at the packages, all these packages are in a different session. But here are the pins, and then the pin, the dimension of the pin, the IC here on this side, and the dimension of the IC on this side. These are all the things that basically you get from the data sheet. So you would have to really go through the data sheet for this component as we go forward. We're really just touching, touching the waters. Now here is the decoder multiplexer that we look at. So the decoder again, it's a the decoder in two forms. What it is, if you look at it, it has ABC input, and then here 8 of the outputs. So depending on the ABC value, if it is ABC 000, that would basically enable the if they are all 00, it will enable Y0. And if they are all ones, it will enable the Y7 value. So if it is 1, it would enable Y1, etc. So it would enable all these 8 pins. And these are the control pins, the selector pins, and the enable pins. We look at the truth table in a while. But essentially what this decoder, if you see, is basically it is decoding the value that is passed into one of these 8 lines. Right? That's a decoder. Typically where it was used in the olden days, it was used for the memory decoding and all. But these days, it's done at the software. So here it is, the enable G1, G2, and GB. And let's look at the truth table here. So here, if they all are high, it's basically Y7 is low. So it is a complementing input. Right? So if all of them are high, the Y7 is low. If all of them are low, Y0 is low. That's when H1, G1 and G2 are held high and low, H and low respectively. Where H and L, these are given. If G2 is H, they're all held as H. And if G1 is L, then also they're all held. Right. Whatever combination that you use here, H on this side and ignore it. When we hold G2 to H and R G1 to L, they're all basically turned off or essentially set to high level. So that means there's nothing that happens, no activity. So if G1 is held high and G2 is held low, then the decoder works and the LLL, all zeros here, basically gives it 0 here on the Y2. Right? So this is the truth table of the decoder. Not much to see there on the data sheet. The voltage that works on the TTL voltage, 5 volts. Basically, it's a 5 volts chip. It's not the same as chip. Then VIH is 2 volts. Anything more than 2 is basically considered as 1 volt. Those are the TTL. You can remember the TTL levels essentially. So these are the things that if you are using it, you can.
So actually we have to remember by heart all these voltage values and all, VIH, VIL and all.
You
For
don't have to buy heart. No, you don't have to buy heart. You can, when you are designing it, you can take a look at it. When this would come into picture is, let's say you are driving the output of this decoder into a CMOS CMOS is basically up to 3.0. So that's when you have to carefully look at the voltage. If you are connecting to another TTL, you don't have to even look at this. And then TTL to TTL, if you are connecting, then no problem. If you are connecting from TTL to CMOS, you have to verify that 2 volts is not going to be too high or too low for the CMOS. The input of that you would see. Right? That's how you would do. Let's say you're driving this with a CMOS IC. So you have to ensure that the output on the CMOS, VOH definition of CMOS is basically is more than 2, than only 2. But you rarely do connect CMOS and TTLs together, but once in a while you might come across, then you would use it. Otherwise, TTL to TTL, you blindly connect it because potential that this is only
Same
for the
voltage level.
yeah, correct. So there is no need to remember. So that's the decoder. Now let's
Okay, so
look
the
at
main things in the data sheet that we need to take care is the operating frequency and all these operating voltages and in the high level, low level voltages, all those. That is the main thing. And the functional, that truth table, that's all right, in a data sheet.
Correct. At this level. But then as we go forward, more complex circuits, they will have a lot more things about the features and how do you use each one of the features. We have to set a reference voltage out there. Those are all given in the data sheet. When we use for the regular ICs, we get to it. There may be more in the data sheet as we go forward. But creating this habit of reading the data sheet is what is recommended here. So here is the multiplexer. Sorry, this is not multiplexer. The BCD to 7 segment decoded by driver. So it's used this way. So there is the 7 segment. If you look at 7 segment, here is the 7 segment. Right? The segments are numbered here. This is A, this is B segment, C segment, D, E, F, and G. And with this, you create all kind of numbers 0, 1, 2, 3, 4, 5. Right? These are the create. So, what BCD to 7 segments segment, you remember, this is basically, it takes the ABCD inputs and generates the ABCD EF. This is a kind of decoder, but not the 1 to 8 decoder that we have seen. But it's basically, depending on say if it is 0001, that means, sorry, 1000, that means the value of 1. For 1, it has to enable B and C, so these two will be enabled. All the other will be off. So that's what this IC will create. And then these are the selected keys. Here for 0, 1, 2, 3, etc. For all these are the values. These are the 7 segment decoder. And the 7 segment decoding will only work with LP and RBI are both set to H. If LP is set to H, RBI is ignored here for all these cases. But if it is set to H, and if it is also set to H, then they all will be basically zero. This also should be ignored actually. Anyway, so they are H and L. Then okay, that's why if this is H and this is L, then they will all be off. That's how you use it. But 0, so you have to ensure that this is off. So this is the truth table. And that's how it's decoded. These are the things that we have done in this digital electronics. How you enable the internal block diagram of the package of the IC. How each of the outputs is generated. So that's about the data sheet for the current segment. If you look at here, again, we're looking at system diagram. In the system diagram like this, there is basically no chance for us to use discrete components. We generally don't use any of these. But another component that we basically basic element component is probably memory. Right? Memory is something that we have. Okay? Here is some memory ICs that we're talking about. Memory is also again a basic. And such a basic memory, we don't really try to find a basic memory element. But then here is also connected memory. Here is again on the mouse, we can select from this whole bunch of memories here, depending on the organization, how it is organized, or every bit, and then the package sizes, and then product type. So one memory that 2 GB NAND memory, NAND flash memory. Here it is. So okay, NAND flash memory. It is organized as an X8 by 8 as bytes or as organized as words. Here is the part number. That means if you look at it, here are the part numbers. This is one part number. This is another part.
What is the part number?
Yeah. So part number is basically by which we identify the IC, right? So this data sheet is for five different ICs. This is a different IC, and this is a different IC. So the part number we are looking at, the way the part number is selected is typically by this. So all these data sheets you will see this. MT is micron transfer micron technology. 29 is the series of the IC that we select. Here is the density. So by selecting here 2G or 4G or 8G, we are basically telling what is the density of it. That means how many gigabits are there. Please note here, it's a gigabit here. 2 gigabit or 4 gigabit. So by that we select 2G. If we look at here, this is basically 29 F2, F4, F8. So this is 2 gigabit, 2G 2 gigabit. This is 4 gigabit. So that's how we select the part number. And then we can also, depending on what we want to connect it as an 8-bit based on that we will of the number of CG. Okay, chip enable. Some of them have 2 chip enable, some of them have single chip enable. You can actually select something with a single chip enable. But yeah, sometimes people use 2 chip enable. Let's say if you are using two of these ICs, then we use 2 chip enable. One enables for one chip enable and the other enables for another. That's how it is. And yeah, there are more of them. This is basically the temperature range. If you use VT, it basically extended temperature, minus 42. Right? If you leave it as blank, it's 70 degrees. So this is how the part number is found. MT29, F3G08, ANA. Again, for the voltage, there is no option. This is always 3.2 volts. Then D, this is first generation drive. There is no difference between the drive. And they didn't tell us what the difference between the drive. So,
what is it? Generation die? That ABC.
This is when they manufacture the chip. I think they are using different generations of the drive. We don't have to really worry about it. Yeah, it's only means something to them. They don't tell us really what will be different. And also, I think it's even often something manufacturing for him to recognize we are doing from generation 1, but that won't matter in the electrical design of the IC. Here is the package code. This is matrix for us for the code designer, which is whether it is TSOP, okay, this is also R48 pin TSOP. They're all TSOP. So it's whether it is lead-free or what is the lead-free is essentially some of the countries essentially mandate that the electronics are made of lead-free. So if you are manufacturing for countries, you will have to use an lead-free. For example, Germany is on lead-free. So you have to use lead-free device. So that's how it is. The manufacturing. This is the data sheet for the memory, the block diagram, and what the pins are. Here is the description of each and every. What is the ALU? ALU is the address latch energy. We'll basically when we are reading about there is a session on memory interface. During that we will basically discuss about these things. But this is the description of all the pins that are described here and the addresses. Here is the address mapping, how it is going to be the address mapping. And since it's an AND flash, basically talking about the block, how it is basically organized, you can actually read by block read and the array addition. This is all the, so there is a lot more involved in these from here forward. That we have, and then the timing diagrams I did, timing diagrams, and about different other commands. NAND flash has commands with, and this is all the description of the command. And the electrical, here are the electrical commands. The voltage 4.6 volts. Takes mean, it takes 4.6 volts. Maximum of up to 4.6. So democracy, it can go up to 4.6 volts. So really, the latch time, holding time, set of time. So anyway, so this is how data sheet of a modern memory is going to be lot involved in it, right? So that covers the basic elements of electronics that we basically use in it. And here is another. This is how basically once you select what it is, once you, this is to show a little more. Once you select a NAND flash here and you click on this thing, it will go, you will get more details about that flash. So here is such an image. When you click, you get compared like, so here is the NAND flash and you get the cost of the IC here, cost of the IC 726 rupees. And if you are purchasing in 10 volume, they are selling it at 600. You are buying them in bulk, like 500 at a time, each at the price by publicity. So cost is always basically a selection criteria for the ICs based on the cost. What is the low cost available for the features that you want. And here is the specifications of the IC, operating temperature range, and the supply voltage minimum and the maximum is 2.6 volts. And then the memory size. So the specification here, and more of the specification. And this is where you can click and get the data sheet of it. There should be link here to the data sheet here, 129. This is the data sheet basically. If you click here, then you get it. This is how you actually go on to the. Here is another, again, the PCB symbol footprint. Those are some things that for the arcade capture we use. So this is where the CAD models are basically, you can actually, so the manufacturer basically, these part resellers basically have these kind of PCB symbols and all the for it on. If not, you will create it on your own when we go to the arcade capture. Yeah, but I'm still trying to see where the data sheet is in the browser for the flash data very good. We go here 29F, I think. It's series data sheets here. There are 18 data sheets. Basically, okay. And here are some more links. Here are links. Yeah, we're done about the session on the basic electronics. One here is something on operation amplifier. It's much more elaborate on the operation that you can go to. Of course, not that we will be using operation amplifiers in our designs in this course, but then something for if you are interested more in operation amplifiers.
So op-amps we will not be using.
Yeah, for a microcontroller based design, typically you don't get to use that. I don't see anywhere we have used an op-amp in our all entire discussions. So we won't be using it. These are all basic, right? An ADC will have an op-amp inside it, but we don't use this. Yeah. This is only for us to refresh and test the waters, so to say, and then just getting warming up into the steam electronics. Rather than that, whatever we have
So the main
reviewed here.
things that we are using is these flash memory, ADCs and timers, ADC DAC, memory and timers. So the main things.
And then we'll use USB 5, RS 485 drivers and those kind of things. Whatever is shown in those are the things that we basically more elaborate. Bluetooth, what you call Bluetooth modules, Wi-Fi modules. Those are to really create a system to integrate all these ICs and create a real system, a functional system, not on the discrete. What we are really using today is all discussed all today at discrete form. Right?
Okay.
Yes. Any questions on this today's session?
No.
Right? Today's session is basically an voltage source, current source, and secondary power supply. Basically, a good power supply is kept with the supplying 2 times the nominal power supply. Whenever we are designing a power supply or selecting a power supply, we want to ensure that 2 times the nominal requirement is capable by the power supply. Right? This generally rule of thumb. But some people will have 1.5 times the nominal requirement. You always have something more than nominal. Voltage source, what is we all know voltage source is basically applies a constant voltage, V out. An ideal voltage source will not have any series resistance, but then a practical voltage source have some amount of series voltage. That means some voltage is dropped across this. When the current goes high, it basically as the current goes high, the drop becomes slightly more. This is basically observed. So most practical power supplies are designed for a specific and a specific voltage. It can supply up to, let's say, 2 amps at 5 volts like this. Is the specification that's given. That's because this resistance is small, and then if we consume a little more than the current, then the voltage drops a little. Than the rated one. And this is how the voltage source is. And the current source is basically a resistance, parallel resistance, very high parallel resistance the current source will contain. So the current sources that typically you have in the labs and all that, it would have a very high parallel resistance, almost close to infinity. A practical one will have very high resistance. So current source would have infinite resistance or no resistance. This is basically what voltage source and current source is. Now let's say for our circuit we need a specific voltage source, a 3.3 volt. How do we build or a specific voltage source? That's basically going to discuss in today's discussion. Now, based on the form factor, we would see the power supply is basically in a rack mount. Basically, typically has only mains. Battery is rarely there. In a handheld, you have a battery kind of power. And in benchtop, you may have both mains and battery. Perhaps for RTC kind of measuring the to maintain the RTC power supply, there will be some small battery that would basically get. These are the now Primary was we are basically discussing two topics. One is primary power supply and then secondary power. Primary power supply is something that takes AC mains and then converts into a DC voltage. Maybe like 60 volts, 24 volts, 12 volts, 9 volts, 5 volts. Should be able to take load off the board, of all the board requirements, short circuit or voltage, and under voltage protection. These are the things that are basically provided in the mains kind of power supply. And we look at also the secondary power supplies today. The secondary power supplies IC 3.2 volts or 1.8 volts, 1.5, depending on the microcontrollers and the ICs that we select. They need these different voltages. So these need to be developed in turn from either 5 volts or 9 volts. So these are basically called DC-DC converters. Additional requirements of power up order. Here the other features that are required are order of the power up. How do we order the in the sense how do we the sequence of the way the power rails come up is important basically for the microcontroller. When we actually get that, we will discuss that. Battery backup is another thing that we needed typically, and power management. We'll be able to power down a specific power rail and stuff. These are all requirements at this level, at secondary power supply. Now here are some power supplies. These are all primary power supplies, taking mains voltage and then deliver a 5 volts or 9 volts kind of power. They come in all form factors. If you're building a rack mount kind of system, you have these large kind of power supplies that basically will supply much higher voltage and current, much higher current and all. But if you're creating a benchtop kind of thing, these are all available. And if you have a further smaller device, these are really of the size of 2 mm by, and this complete power supply, this takes AC mains and then converts it into the required DC voltage, 9 volts or whatever. This is basically can be directly soldered onto the PCB, and this is also 2 mm by 2 centimeters by 2 centimeters by 1 centimeter kind of size. That means whereas these are basically somewhere around this power supply is about size of 8 centimeters by 8 centimeters by 3 centimeters kind of power supply. The same power supply is available here of this size, but then the current in electronics, the funniest thing is basically the size doesn't matter. At the smallest size, you get what a large size kind equipment can offer. So it all depends on the kind of ICs that are used and all that. The miniaturization really does not reduce the features a great deal. So these are the power supplies that can be used in smaller equipment. If you have to place an electronic circuitry in the switchboard of a home, then you need to use a very small power supply. You use this kind of power supply because within the switchboard there is very small space that is available for electronics. So you need to miniaturize compact things. So that's where you use it. Now,
okay, so what do you mean by that form factors?
Form factor. Form factor essentially means size, basically. Meaning form factor basically means by its meaning is the size of the electron. What is the its dimension is basically what is meant by form factor. So these are although in the image here they are all looking the same size. These are really small. This is 10 mm by 20 mm by 20 mm, whereas this is some 70 mm by 80 mm by 30 mm. This is even bulky. This is almost like this is called a brick power supply. This bigger. So they come in all these different form factors.
Okay, the brick, that brick one, where do you use it? Where
in rack mount, typically in rack mount
Rack mount means what kind of device?
The electronics that basically goes into a rack. It could be anything, network switch, or a PC, a rack mount
Okay.
PC, or rack mount electronics such as communication equipment and all that. That one that fits in a rack. Basically, it is meant to be fit into a rack, right? And so this is typically how a PCB is basically packaged into a electronics. It would have a primary power supply, and on top of this you have, again, if you look at this section, there is some more power pads and stuff like this. This is also secondary power supply, and then some screen and something, some interaction device. So this is how you package everything into a. This whole thing will be packaged into a box and create an electronic system, right? So what we want to observe here, on this board there will be a secondary power supply, and on the here there is yet another from the main. The mains is not directly connected to a primary power supply. It just generates either 5 volts or 9 volts, and this uses that 9 volts or 5 volts and supplies current to all the electronics. So we are going to discuss today what is going to be there in this, right? Okay, before we go to that, some of the manufacturers of primary power supplies are Meanwell, Recom, EFC, Viker. They're all primary power supply manufacturers. In the secondary power solutions, you have text instruments, analog devices, active microelectronics. They have ICs for the secondary power supply. Let's say one of the exercises is to select a power supply, 5 volts, 25 watt power supply, and 5 volts, 5 amps, 12 volts, 2 amps. This is dual power supply, basically 5 volts at 5 amps and 12 volts at 2 amps. Here is the Meanwell website. We can actually go onto the Meanwell site. It has all these many different varieties of. Here is we said we wanted to basically select a 5 volts, 25 watt power supply. So 5 volts, 25 watts. Let's look at these power supplies. Yes, there is single power supply, 25 volts. RS25, I think that's probably sounds like a 25 watt power supply. And the other power supply we wanted to look for is 5 volts, 5 amps, 12 volts, 2 amps. So it's about 50 watt power supply. Yeah.
See, these model single, dual, triple means what does it mean?
Yeah, we are looking at
5 volts,
dual
5
means
volts.
it will have dual will have dual power supply. That means, for example, if you here our requirement is to have a power supply of 50 watts. Out of the 25 watts, 5 volts, 5 amps, and another 25 watts, 12 volts, 2 amps. So we have a 12 volts as well as 5 volts, a dual voltage that's coming out from the. Yeah, here is a dual power supply. So this is channel 1 and channel 2 on R50A and R50B. Here 5 volts power supply, 5 volts and 12 volts are there. 5 volts at 6 amps, so that comes at 30. 12 volts at 2 amps. Is the rated current. So this is exactly what we were actually looking for here. If you see 12 volts at 2 amps and 5 volts at 5. But we got 5 volts at 6 amps, so it's slightly more, so it will meet the requirements. And total of 54 volts roughly. So we were looking at it to and current range is 0 to 6 amps, 0 to 3. So some of things that to look for, basically the ripple and noise. This is 80 millivolts peak to peak ripple, and on the 12 volts it's higher, 120 millivolts peak to peak. If the ripple, you want the ripple to keep as low as possible. That means the ripple noise 8 millivolts peak to peak ripple. Of course, once you basically create a secondary power supply, then the ripple will actually come down. Voltage can be adjusted between these two volts with a pot setting Let's say you can adjust the voltage, like that arrangement is there. Voltage tolerance 2% is the voltage tolerance. This is how fast it would basically come to set up as right at 230 volts and at 150 volts. We apply to 30 volts. How fast will the 5 volts power supply will come up? That's basically what we set up. These are not really a great deal of requirements in power supply, but the important requirements are in power supply is. So we want to see if there is an overload protection. That means if it is taking more than 5 amps, then what will be the protection type we pick up without automatically asking for it. So it will basically get turned off if there is an overload. Similarly, if there is an over voltage, the voltage is because more than that, it will basically turn off. So that's basically the protection that is available. And the other things that are efficiency is another thing. If you see, this is only 78%. Then this 79, based on the kind of power supply that it is, its efficiency is there. And the other thing is basically you want to look at is power factor also. Let me see if there is power factor specified somewhere.
So if overload is there, automatically it will turn off.
Yeah. Correct.
So everything actually, it suddenly turns off means it's not good, right?
Yeah, basically I think it doesn't turn off. It basically reduces the current to 5 amps. Basically, whenever the overload is there, it will have a glitch in it. The pickup mode is there. It will not have a turn off, but it will basically instantaneously there will be a small glitch that comes up. But then if the load is too high, then it will automatically turn off. But then the load needs to be need to be regulated. Right? If the load is not correct, something is wrong. So powering off is the best thing to do in that condition.
Okay.
But if it's a microcontroller board, for whatever reason, if there is due to power supply problem, if it goes brown, microcontrollers have something called brownout. Whenever there is a brownout, the microcontrollers have certain action that they take. Brownout conditions. They basically typically interrupt launches during the power is going down. Quickly it will service an interrupt and then automatically it will shut off. Microcontrollers have brownout, features typically for those conditions where the power supply suddenly turns off. Here it's called hiccup mode, so I'm thinking it doesn't turn off here, this one. But nevertheless, there are power supplies that automatically turn off if the load is too high. That is because the load should never go high, right? The load needs to be regular. So if there is a short circuit that happens, then the load goes high. So that's not a good condition. So turning up the power is the best option because efficiency, then AC, then inrush current, leakage current, there is small leakage current of 2 milliamps. And here MTBF, how often a failure can happen. For about 172 kilo hours, you can expect a failure may happen. So very high MTBF, right? Mean time between failures. So they're all for safety equipment that you can have. And then
so MTBF means that for this much time it can work, or what does it mean?
Correct, yeah. It's basically an average specification. It's not exactly that it would basically fail at 172 kilohertz. But between two failures, the average time between two failures is this much. That means if in the course of a failure to occur, either because of a component failure or whatever, that can occur between this much of time. A very long time.
What happens if failure occurs? It will restart again, or what?
Failure occurs depending on the type of the failure, the power supply will fail. It may be that it will not deliver the 5 volts, but it will deliver maybe 10 volts, or maybe it will deliver 2 volts, or it will not deliver any voltage. It will completely be turned off. It could be any failure, depending on what failed in the power supply. Could fail. Could be in an open circuit, and anything can happen. That is basically a failure. So it essentially says basically the idea of MTBF is showing here that it doesn't fail really. That means if you put the system into usage, then he's saying 172,000 hours, but that's more than few years basically.
Yes, yes. Okay.
More than few years it will basically put into the usage. It will basically work for few years. If you completely keep it on, then it will take that long to fail. Is what it is.
Oh, yes.
And a failure can be anything, some vibration. And they didn't give a power factor thing specification, but that's also an important specification, power factor. That means for the mains usage, basically. Of course, it's again not an important specification also, power factor. From the mains, if you have some, 98%, you don't have to really have 98% power factor. But if you have the 60% power factor, you're drawing more current. But from the main, you don't really worry about this level so much about. And some of the data sheet also has the size, dimensions, and all that. To plan your mechanical enclosures and all that. So the dimensions of the power supply is all.
Is it actually required, and while we design, is it necessary that we should keep this dimensions and all?
Correct. Yeah. What would be the size of the box that you would actually use? So if you are using like, let's say you're building a typical system with this power supply and a PCB and this, and you're creating a box, so you have to look at the dimension. So a hardware engineer would also basically, he may not draw the cat diagrams and all that. He may offload the mechanical enclosure to somebody else, but then he has to specify, what will be the dimensions of it and what is the minimum dimension of it. So that's the reason in hardware engineering also need to look at these aspects while they're designing the hardware. What is the size of the box, and so we get to do that. May not be a major part of it, but then it's also important to see the dimensions. So as a hardware engineer, then you can one need to look at those. And here is basically we look at these kind of power supply designs a little bit when we actually go into the primary power supply design. We look at what is switching, the rectifiers, and all this. But this is the block diagram now. And then with the load, he is showing the current at 5. This one right here at derating curve. So it basically supplies 100% until 4.5 amps. So until 5 amps it should have been. So somehow it's shown. Maybe it's not very accurate. Until 5 amps basically shows this way. Until 6 amps maybe. After 7 amps it basically falls down. Overload it basically cuts off. Basically it cuts off this. For overload, anything over 7 amps. So here, let's look at the 5 amps. So that's how we select power supplies from that. Then let's look at secondary power supply design. Here, this is schematic. Let's look at arcade software. Basically, let's with this in an arcade software, you can actually create a new page and run through the arcade here. You create new. This is how you create a new project or a new design file. Once the new design file is created, you get this something like this without these pages. And then you go here and create a new page. It basically creates a new page. And then here the page 0 is created. You can actually give the page a name also. Some conventions are very individual. I typically use page number and the name of the page. what it does. So here to place a resistor or component, you click on this icon, and then basically here, then let's say resistor, I want to place, click OK, there is the resistor. You click here, there is the resistor place. And you click here and right click on the mirror horizontally or rotate, so it basically comes horizontally. After that you can say end mode here, and here is the connection connecting. You click on that one, click again left mouse button, click, that can get connected to. Similarly, click on this left mouse button. This is how you connect them. Let's say we want to place now a small component, let's say, and let's let's take this comp and click OK. So here it places this component. Looks like a microcontroller, and W400 microcontroller. And here is the U number that comes automatically. So we can change the U number, the number also. Let's say this is first IC that we do this. And then let's connect, and let's say we want to connect this DQ here. So this is how you can, even this one you can actually rotate and place in the flash. Control Z to undo, Control Y, Control Z to undo. You can actually boom these schematics by pressing here. Very simple, there are not many controls. Now you can always, once this is R4, let's say we want to change this, double click on it, and here change it to R1, change this to R, and we can actually display both value, here, it's actually value based. So the value and name and value is specified to value key, let's say 1K or 200, generally potentially value. So that's how we basically can actually, you can double click on it, it opens here, you can actually edit it here, or click on this one, then you can edit it here. And so R40, let's say this is R4, and value is 1K. So that's how you can edit resistors, and then you can actually place capacitor. Yeah. So I have the library here. Basically, this is where you are placing all the library of components right here.
So lots of components are there, no, in that. So how do we know which microcontroller we want, which resistor we want, and all those?
Yeah, that's the thing that we basically go through this course. By end of this course, right? Hopefully you will basically learn which microcontroller to use, which component to use, etc. And the
So
library does not. If the library does not have the component, what do you do? Right? If the library does not have a component, what do you do?
okay.
Right? So we look at all those. Just we want to place a decoupling capacitor and connect it. And then you also have ground connection here. You take it ground. So this is how you connect to that. And then if you want to edit one of the parts, let's say this, we don't have a part symbol in the library, then we have to create it on our own. I'll show it probably next day. We will have to, most often you don't find symbols for the microcontroller. You may have to create it on it. It's an elaborate process, but we can create that out. Actually, I thought I would show it another day, but then you right click on this and edit part. Edit the part. So this is how it comes in. And then here, basically, you can drag it, and then let's say we don't need this pin, delete it, select them and delete.
That is actually a standard microcontroller. Like, so how can we edit into that microcontroller? Because it's standard, right?
Yeah, so we will actually, we are creating a new pattern, right? So we change, let's say this is STM 32, and we are not changing that. We are changing and saving it as a different test. That's basically what we're trying to do. And then these, you double click on this pin. Here, let's say this is, this, let's say is ground, that's GND, right? And click on this, let's say this is VREF. So we change the pin numbers, and let's say this in a VREF is an input. Yeah, let's say, suppose it's not an input, so we make it output. And then pin number also we can change, let's say this is pin number 12. So that way we change every one of them, and then the close this. Then it will ask whether to, okay, this is an error. Now this will say update the current one or update all. Everywhere you want to update it, or update only the instance that we actually clicked on and clicked the edit bot. That one. So we say only want that one we want to update current. So here it is. It got now reduced number of pins, and then VREF has come here, ground has come here. So that's how we edit the part. This way we can create new parts, and then these new parts can be used in the schematics. This is the one, and there are other features of this. You can actually put a note here for your purpose. This is the line. So that's how we can actually put it. And typically the schematics here have these standard stuff, the title of the schematics, and you enter the document number of the schematic and the revision code. Let's say it's 1.0 or 2.0, whatever is the revision. These are the things that need to be created. The date automatically comes in March 16, 20. So this is how it is. You create a page, and then when you close it, it will ask whether to save or not. So you save. So there is page 0, page 1, this is page 0. So this is how you create different pages, and then let's say you want to connect. Another thing that to remember is the off-page connector. So let's this one right here. So off-page left. So I take this and connect here. Let's say one of these pins we want to send it to the another page. So we connect it here with an off-page connector, and we call this, let's say, RBN. So this RBN1 can be used in another page. This is how we connect off-page. These are basically either this can be connected here RBN1, or we can actually even take this RBN1 and connect it here out, and we connect that to here. So some things we can basically don't have to take it around like this. We don't have to take it around this way and then connect it. Sometimes you can do that, or sometimes you can actually connect it to a connected page, not a connected to a port pin, and then connect that port pin back to it. That's how we do it. And the same technique can be used to send the net to another page. We can actually send it to another. So there you go. So this is how we can, and then in another page we can actually use RBN. Let's say we take RBN here and it goes somewhere here. So we can put RBN here and then connect it. Or if this is the RBN, we can rename this to RBN. So that gets connected to this page. That's how we interweave from one page to another page, right? So this basically what is there to the schematic. There's nothing more to it, really. There are a few other things that we will see later on, but not right now. Not to really make it really cumbersome to understand. So I'm keeping it simple. That's basically all. That's how you draw the entire schematic. So now let's look at the FPGA power supply DC-DC converters. So one example, the power supply design. This is the power supply design for this microcontroller board. If we look at this, basically these are all DC-DC converters. DC-DC converters. And if you look at the VCC 3V3, this is 3.3 volts. This is 1.8 volts. This is 2.1 volts. 5 volts. This is 1.2 volts. This is a TPS 73701. This is TLV 7001 and TLV 70025. These are the part numbers. TPS 73701 again. And these are the part numbers for the power supply. And so this is the power supply.
These part numbers, do they have any specific meaning? Like TLV 70025 means like, does it mean 25, something like that?
Yeah, this actually means 25, exactly. This is 70025, means 25. 700018. That's again TA convention, but it's not a standard, right? You don't, here, it just happened to be here, they use the standard here. But otherwise it will happen. 7301 is a generic, is a programmable part. So we'll run into that in a short while. That means its voltage can be programmed by the voltage ratio here. This resistor divider here, 52.30, 52.3K and 30.1 will basically create. What I will do is basically let's look at a programmable voltage. Programmable voltage. Yeah, this is here. TPS 62120 is basically the same kind of power supply ICs. This is a power IC, power supply IC. So TPS 62120 we will look at. Let's look at the data sheet of TPS 62122. Okay, let's look at 62112X is what it is. High voltage efficient buck converter. So this is how to use this in a schematic. This is the standard schematic that we have given. This is the V output. V output comes here, coupling, decoupling capacitors. Across the power rails, usually you have these capacitors that are connected. He's asking us to use a 4.7 microfarad capacitor. It essentially reduces the peak, the peak noise, the noise that comes from, regulator noise. Basically, there will be some small ripple noise. That ripple noise it will reduce. Also, if for whatever reason a component suddenly draws more current and then later on doesn't draw the current, those fluctuations to ensure that those fluctuations do not create noise, these capacitors are added because it's a network of connections. In those connections, when those current flow, there is chance that there is noise basically we can generate. So this decoupling capacitor always need to be as close as to the pin. There, one of the things that basically when you tell the layout drawing layout artist to basically put it close to the pin, meaning put it close. Now something. So this is the data sheet. Let's look at the features. Basically wide input voltage range 2 volts to. So if you look at it, this is not a fixed voltage. You can program it from 2 volts to 50 volts. If you want basically a 9 volt, you can generate a 9 volt out of it by supplying a more current. It's a buck converter, so at the input you have to supply 15 volts and then you can generate a 9 volt out of it. That's it. And 11 microamps percent current. That means when there is the load is not there, it basically the 11 microamps is all its output current. It can supply maximum of only 75 milliamps. So you would have to, for whatever reason, if it's drawing more than 75 milliamps, this is not enough. So let's say your microcontroller, let's say we are generating 3.3 volts using this, and then the microcontroller draws 100 milliamps. This part is not enough, because this can only supply 75 milliamps. So you have to go and search for one other part that will meet. This is how we have to ensure that if it only draws 50 milliamps at 3.3 volts range, then this is good enough to use. And this uses a switching converter. That's why if you see it's a 96% efficiency. We'll know these a little more in the next power supply design. So it's not basically an LDO kind of power supply. Just do not drop the voltage, but it uses something called switching, 800 kilohertz switching, and so it is very efficient, almost 100%. Then it's basically this is the SOT 8-pin size, 2 mm by 3 mm size. It also comes in DFN 6-pin package size. Those are the packages that are important. SOT 23 or SON 6 package. These are the two packages that it is available. It works in the range of -40 to 85 degrees centigrade. And then it also has an enable pin that will basically, if the enable pin is on, then only the power supply comes. If you turn it off, enable pin is set to off, then there will not be any power supply output that will be generated. Here, so conveniently connected to the input. Input can be anywhere from 2.5 to 15 volts. So let's say if we connect a 9 volts here, or a 9 volt, let's say we connect 5 volts here and program these resistors. R pull up is 100 kilo ohm, and this ratio of 300 kilo ohm by 240 kilo ohm. If we set it so that it generates 3.3 volts, it will generate this. So this formula is given somewhere elsewhere in the data sheet. Here are the packages, and then in this package, the SON package, there is a thermal pad. So the thermal pad needs to be connected on. This needs to be connected to the ground. The thermal pad connected to the ground. That will dissipate all the heat that it can do. Here is the description of the pins. Ground is ground. Feedback is the feedback for the regulator to regulate the voltage precisely to whatever voltage it is, 3.2 volts. This is a PG pin is a power pin output. This pin is available, it's an output. So it tells whether it is power is good or not. This can be given to a microcontroller. The microcontroller watches whether the power supply is okay or not. This is the S ground and SW. This is the switching pin, MOSFET switching pin. This needs to be connected as the. This is the voltage input. So that means you are giving the output from a primary power supply. Let's say you are giving a 9 volts here, and at the V out we are getting a 3.3. These are the descriptions of those, and basically the maximum ratings. Vn maximum can be 17. You cannot supply more than 17. If you connect it 24 volts, it's going to burn out. It's not good. So here are the specifications of those. I'm trying to look for, here is how the V out is calculated. V out is VREF into 1 plus R1 by R2. VREF is typically you take it as 0.8 volts. So it's 0.8 volts into 1 plus R1 by R2. That's how you will get V out. So from this, you can calculate R1 and R2. If you take a value of R2, let's say 100 ohms, then you get R1, the voltage. R1 maybe whatever it is at your point. Basically, you type in, put it into the calculator and you get. And to minimize current.
VRF value is this 0.8 volts. It is fixed.
It is VRF value is 0.8 volts. Yes.
In all the cases.
In all the cases, correct. In all the cases, take it as 0.8 volts and then calculate. And then he is giving additional recommendation here. R2 should be within the range 82 kilo ohms to 360 kilo ohms. So you always select a kilo ohm resistor, somewhere a 100 k ohm or something, so that the current through the feedback divided network should be within the range of this, and that's the feedback resistance, not the R1 R2. And R1 and R not exceed approximately 1 megaohm. Their values shouldn't be more than 1. So these kind of.
capture that you shown, so in that there will be these buck converters, right? So we just can take that and put it in the schematic, right? There will already be these buck converters in that schematic, right? You showed,
Yeah, correct. So this is how it is being created from that part.
Sometimes if we want different layouts, means we can design R1 and R2 according to our, that's what we're saying, right?
Correct, exactly. So let's say we want basically a 1.8 volt derived here. So we calculate the R1, R2, here R27 and R2.
Okay, so then we put those according to that, like you showed earlier. What
correct.
Can give the value in that.
Yes, correct.
Okay.
Correct.
And what about the capacitor value?
So the capacitor, he would actually give it there. It's a 0.1 microfarad.
Always.
It's a decoupling capacitor, and here a 1 microfarad. Really, he suggests that also. If not, basically a typical 0.1 microfarad can be used. It's a decoupling capacitor. We can use 0.1 microfarad or even 1 microfarad. Here he has specified as 4.7 microfarad per ohm. So 4.7 into CFF, he has given R1 and CFF places a 0 in the feedback loop. CF is required for optimum regulation performance. He didn't specify, just use any value point. CFF also he has specified actually. The CFF value for CFF can be calculated as 1 by 2 pi into R1 and specified. This is how you calculate the CFF value and CFF value. So that's why it's necessary to read the details of the data sheet. And inductor selection, there is an inductor also if you look at it. Here is not in this one. I think this one didn't ask for an inductor. Here he has put in an inductor in this schematic. Here is 22 microhenry inductor. This is switching. This is a switching type regulator, DC-DC converter. These are an LDO. This is an LDO type of converter. It's basically not 100% efficiency. This is not 96%. Anyway, the efficiency we'll discuss in a short while. So the 22 microhenries, that also he has given a calculation. He's asking to use a inductor base. The calculation of the inductor also is inductor value. So you calculate the inductor value that way, and if not use that 22 microhenries. The device is optimized to operate for an output filter of L22 microhenry. So you use microhenries. This is what you use. But it came as this calculation. From that you actually calculate the switching current IL max that basically goes through the switching SW pin. This is the current that goes through the SW pin that he is basically selecting here. So that basically completes this IC. Then the dimension, how basically with V voltage, how it changes. He's saying the efficiency, how the efficiency will change with respect to output current is also shown here. More output current, it's more efficient apparently. For higher, lower currents, it's not all that efficient. It will not, because its quiescent current is there, so it's not as efficient. Anyway, this is a curve that you may not require to use. These are all efficiency curves. So, during the turning on, how the power actually comes up, that's shown. V in is applied this way, the V out basically comes in. Lot of curves that we have seen. This is the standard circuit. And of course, it's also can be used in many other configurations. There is same he has given for 3.3 volts. What are the values? He has already calculated the values for 3 volts, 2 volts. These are the values for 1.8 volts. He has given those already. And here is the precaution for this. Some of the things that basically to remember is basically the capacitor. The capacitor need to be as close as possible to the pin. So this is how we place capacitor very close to the pin. Don't want to connect the capacitor somewhere far up, right? Similarly, the capacitors need to be as close as possible. And the example. And here are some guidelines. Basically, for this specific pin, is basically use a common power ground node and a different node for the signal ground to minimize the effects of ground noise. To basically reduce the EMI EMC noise, to basically asking to connect a common power ground and a different node for the signal ground. So he's basically saying this ground plane here, the ground plane, he is asking don't connect it with the ground plane of the signal ground. Signal ground will have a ground plane. When we discuss the ground plane, we'll see that. So he is asking to use this ground and separate from that ground. Don't mix this ground and that ground together. Of course, they will have a common connection somewhere, but don't mix them into same ground plane.
What is power ground and signal ground? Like, can you show in this layout? Like, what is power ground? Means all the power supply grounds and output
correct.
signal ground.
Correct. All the power supply grounds will come and get connected here to the ground. Typically, when we discuss in the layout, I think it's too heavy to discuss. But then, there would be typically you will use a ground plane. A ground plane is a separate layer, and in the layer we will use a ground, and that power ground will actually connect this to that power ground. This pin goes to that ground, and so that ground and this ground need to be separate. All the signal ground, let's say, would come up to this point. A copper plate basically in the ground layer. That's for the signals. That means what is the signal ground? Let's say if you look at it, this is all power ground. But if you take a STR controller or something, STR controller, any ground that you see is the signal ground. It's not the power ground. That means you're basically running high speed switching and all. These grounds he is asking to basically connect to elsewhere, right? Elsewhere, not combined with the power ground. For example,
So
these are all
here
signal grounds.
these and all having same grounds, VDD, VSS.
This is the signal. Yeah, if you see, this is signal ground. So this ground need to be separate in the layout. So as we go forward in the layout, we will discuss this. So to reduce the EMI EMC noise, just to remember, I mean, next time we discuss, it will be more in depth. But this time, just to understand that during this, he would actually give layout instructions, and we follow the layout instruction. Right? In the next time we review it, we will review it in depth. So the signal ground and power ground, he is asking us to keep it separate. So this is how the layout instructions they would give in each one of them. We follow this, and the packaging, the dimensions. This is for the layout purposes. The layout artist will actually take the time. This is basically 1.3 mm is what is available between these. That means 0.65 mm between this pin and this pin. 0.65 mm is fairly doable in Hyderabad and those kind of locations. People can easily solder it. 0.6 mm. If it goes down to 0.4 mm, you may have to find very high scale labor, or you have to find a pick and place machine that can actually do that kind of pitches. So 0.6 mm fairly doable anywhere in any city. People can do it. So let's go back here. This is a programmable power supply. So that's how you actually use the programmable power supply. There is a power good output that can be connected to interrupt pin of the microcontroller. When we look at the microcontroller, we'll actually discuss it again later. Here is fixed LDO Here is the TPS 760PD. This is an IC. It simply it can fixed output voltage is 5 volts, 8.8 volts, 3.3, 3.8 volts, 3.3, 3.23 volts. It can generate any of these fixed voltage. They are basically given here. TPS 76030, the part number, or if you go here, 3 volts. TPS 76030 dBVR. This part number is for 3 volts. This part number is for 3.2 volts. This part number for 3.3 volts. This is for 3.8. This is for 0. For all these, it's the same data sheet. This is how it is. It will have an LDO kind of information and the current limiting, right? And a thermal sensing that would automatically shut off. If it becomes too hot, it will basically automatically shut off the power because something wrong with became hot. So it is power thermal sensing, right? It would basically give it an ESD protection. It can operate from -40 to 125 degrees. Thermal protection is there. Quiescent current of 1 microamps, very small microamps of when it's not being supplying to any of them, it will be only 1 micro. Here are the nominal and maximum that you can connect for the input. Input voltage you can connect up to 16 volts. That means you can connect even a 9 volts or a 12 volts primary power supply into this. Or a 15 volts power supply can be connected easily. And then you can generate. And you should not exceed 16 volts. Right? The typical output is 2.96 to 3.0 volts for this one. For TPS 7602 is 3.2 volts. So he is giving that. For a current of 1 milliamps to 15 milliamps. Anywhere between those range you can get. And one more thing that we missed is basically I think it's only up to 50 milliamps. Right? And he has conveniently kept the efficiency. It's not going to be, it's an LDO. LDO is definitely not going to be an efficient one. It will be typically 50%, 40% or 50% efficiency. That means if you supply 100 milliamps in the input side, it will generate a 50 milliamps on the other side. So it will draw 100 milliamps to supply 50 milliamps. So it's not as efficient.
Then why are we that it is not?
But it is a simpler circuit, and the power supply, probably sometimes you are not bothered about, where basically the mains has so much of power supply. Your fans and regulators, they'll use much more, from drawing from the mains. They would draw much more current compared to electronic. So we simply, hey, what is the point in worrying about making it a complex circuit and all that, and the EMI, EMC and all the switching noise and all. So simple LDO will not have the switching noise. People will use it. You don't have to worry about if it's connected to a mains. You don't have to really worry about the efficiency. That's when people use LDO. Right? The power surge. Here he is asking to use a 2.2 microfarad at the output and then 1 microfarad at the input. That's about it. So it's simple IC that can generate any of these. So in the schematics, basically I showed these are LDOs. Power supply. This one is an LDO. These are all actually LDOs. Even this is also an LDO. They are not switching because the switching kind of thing is not LDO. This is the simply made. The efficiency is not really bothered. And so this is also.
For the second one, then. That.
This is LDO. This is not an LDO. This doesn't have the inductive and all that. The switching related components are not there. It's a programmable rate, and this is a fixed rate. It's a fixed rate. And we'll.
You have shown like all are connected, right? You have not shown it as separate ones, right? Okay, that enable pins are the first one's enable pins are given through a resistor to the out of that second one? What is that connection?
Sure. Yeah. Good point. Typically, in a microcontroller, when we discuss that, it is important that the power supplies to the microcontroller basically go in a specific order. Typically, the core voltage of the microcontroller need to come up first. 1.2 volts need to come up first, then the 1.8 volts, then the 3.3 volts. They need to come up in that order. That means if you first pass on the 3.3 volt and then the 1.2 volt, then it's not going to be the microprocessor is not going to be powered up properly. So what one would ensure is that the 1.2 volts is fully comes up and this 1.2 volts output is connected to the enable pin of the 1.8 volts. So only when the 1.8 volts come up is connected to the enable pin. That means when you apply power supply 5 volts to here, the 1.2 volts will stabilize first. Once the 1.2 volts is stabilized, the 1.8 volts get stabilized. Once the 1.8 volts get stabilized, the 3.3. This is called power sequencing. Of course, in the microcontrollers we have discussed it ahead of time, so there is no problem. We'll come back to
that's it. VCC 2, V5.
yeah. This is the this is the input voltage. This is the 5 volt input.
The third one, you didn't mention that. 1 volt, 8 volt, 3 volt, that is it. That's the third one.
No, there is 1.2 volts, there is 2.5, there is 1.8 and 3.8. These are the ones that will go to the IC. This is the VCC 5 volt, 5V is coming from the connector. That means we connect the power supply connector here and the VCC 5 volts is here taken and it's connected. Right? And there is basically diode protection is given here just in case the power supply is connected in reverse direction. This diode will short it and then the power supply will basically get disconnected. So this is a protection given just so the connector that doesn't get connected from pin number 5 to in the reverse direction. Right? This is a protection. Any question?
The first and second one you explained. Third one is which one? Third and fourth one. That is fixed, right? That's also fixed. Okay. First one is adjustable and the rest 3 of them are fixed, right?
Correct. Yeah. Correct. Yeah, and I think you're unable to see the yes. The first one is 3.3 volts. This is 1.8 volts. This is 2.5 volts.
First enable to the second one's output that you have connected one resistor, right? But in the rest, why we have to connect that resistor? How do we know that we have to connect that resistor up to 6?
Yeah, it's a 0 ohm resistor. It's not maybe there.
It's 0 ohm.
0 ohm. So basically, I think when the schematics was given, in case you want to disconnect this, to disconnect 3.3 volts, this given. To enable or disable the 3.3 volts given, but it's really meaningless. You can connect it directly. If you take out this if you remove this resistor, then it would automatically be not powered up and 3.3 volts will not come. Basically, to debug whether this 3.3 volts is coming or not is basically this pin is given here. Sometimes you may use something like this in a regulator, but it's not necessary. It's a 0. That means there is no resistance. So that's that. Say let's look at this power budgeting. All the these are the guidelines, right? Every IC data sheet for now. Okay, how do we ensure
that every IC is getting enough power supply or not, whether our power supply design is okay or not, is basically this. We have to go through every IC and then see what is the nominal current usage and the maximum current usage that IC uses. And similarly calculate and record for every IC the anticipated maximum current usage. And then we also have to see for what is the power range. Is it the 1.2 volt power range that it is taking that current 1.8 volt, 2.5 volts? What is the power supply for which that current is needed? 3.2 volts. So every range should support the maximum. Maximum we have to definitely support, because for whatever reason the IC goes in different modes and then it can draw the maximum. So it is mandatory that we have to support the maximum that the IC should draw, right? So based on this, we would also calculate the current reflected in the primary side, the 5 volts and 9 volt side. Also we have to calculate, and that's how we select the primary. If the current has come to, let's say, 2.3 amps, and we use one of the power supplies, 2 amp output 1, it will not be sufficient the primary power. So that's how we calculate. That's power budgeting. So here it is in the power budgeting. If you look at it, we have a 110 volts, 9 volts power supply connected here from the main, and then this generates a 9 volts lecture. Here we set a 9 volts or a 5 volts. Let's say this will convert from 9 volts to 5 volts. We used a LDO, let's say used an LDO to convert that 9 volts to 5 volts, and then further given that 5 volts to 5 volts to 3.2 volt LDO and 5 volts to 1.8 switching buck converter, and then again another switching buck converter to 1.8. This is how we have connected this, and this is right. So this is on the board. This is all on the board. This is on the primary power supply. So on the board we have 9 volts to 5 volt conversion, and then 5 volts to 3.2 volt, 5 volts to 1.8, 5 volts to 1.8. And here all the ICs together are drawing 1 amp. They are all together drawing 1 amp. This is 2 amp. At 5 volts they are all drawing 200 amp. Some TTL logic is there that's drawing 200 amp. So this is the power tree, right? This power tree we use it, and then we want to calculate how much current total that needs here. This is 200 milliamps. So the way we calculate, we go to every one of them. V2I2 equal to V1I1 into efficiency, right? This is the formula. The V1I1 I1 we take here. V input and input into efficiency 75% will give this V2. Right? So based on that, if you calculate on that, we can actually calculate the I here. I here will be, if you actually practically calculate, let's say 3.2 volt at 1 amp. So 3.2 volt into 1 amp is into 1 is basically 1 divided by 0.75, 4.2. 4.2, and so if we want to look at the divided by 5 volts. So 0.85 is the just reflect here into the primary as 0.85 milliamps, or sorry 0.85 amps, or otherwise 853 milliamps. So we calculate for this one, add all of them, all the 4 of them. Let's say that comes to, I'm not calculating that, but to calculate memory, add it to the memory, and similarly let's calculate for this one. 1.8 into 1 is 1 divided by 0.98 is 1.8. Add this to memory. Similarly, this is up to 2 amps. This will be 2 amps divided by 0.97. You can take it as and add this to memory. And equal the memory 4.75 plus 200 milliamps. So this is coming to 4 amps essentially. Here, it is right here. It came This 4 amps here has actually resulted into 4.75 amps because of the inefficiency. So 4.75 milliamps here, 4.7 amps, and then 4 point, that is coming to 5 amps only. So this power supply should supply 5 amps. So we will have to design this in such a way that it supplies 5 amps. And then again we apply that here, 5 amps to 9 volts. That may come to some 3 amps or whatever. 50% of it might come to maybe 7 amps or something. So we will have to select a power supply of 7 amps. This is how every point we have to ensure that the enough current is supplied by that IC or by the primary power. This is we draw the power tree, and for each of the power tree we basically ensure that enough current can be supplied. This IC, this 5 volt, should be able to supply for all 4 of them. This is how we do the power purchasing for a circuit, right? For circuit or a system, and that's very important. Otherwise, after basically connecting everything, populating the code, it may be something may be resetting. We don't know why it is resetting. There is no clue. It's usually because the power supply there is some problem with the power supply that it automatically doesn't supply, it cuts out.
So you said some order, right? So it is always in that order of like.
Yeah, it's always from the low voltage to high voltage.
Higher
1.2 plus core voltage first. 1.2 is called the core voltage, goes into the core. The IC basically, microcontroller basically boots up from inside out. The 1.2 volts is basically the innermost, the high speed and the core voltage. That basically need to be, core voltage need to be applied. It's always from 1.2 volts, then 1.8, then
what is that ORCAD capture, right?
arcade captured, yeah, correct.
Yeah, today's topic is basically the second part of the power supply, the SMPS power supply. We'll basically in SMPS we know that there is an increase in efficiency and reduction in form factor. The drawbacks that we have seen with the linear regulator power supplies is it's bulky. The transformer is bulky because of the low frequency and all that. Efficiency is 40 to 50% in linear power supplies, whereas in SMPS basically uses high frequency switching, and so the transformer is small. At high frequencies, the transformer size basically reduces drastically, and efficiency is basically above 90% and can be achieved due to power conversion in SMPS. Do you want to mute your microphone and turn it on when you want to? The typical SMPS, it's not a block diagram, but it's kind of, it's not a circuit either. It's basically typical SMPS basically looks like. This is how the representation of SMPS. It basically, there is a rectifier that basically converts into input AC into unregulated DC, and there is a filter also unregulated DC. Then there is a switch here. Basically, the switch is the one that basically turned on and turned off at very high frequency. So there is a duty cycle control, and basically the switch on off times is controlled by this circuit, basically this IC typically. And this side basically there is inductor and capacitor and all that. So and the load is connected here. This is how basically the SMPS concept is. So what happens here is basically when this is turned on and turned off, basically conversion happens. What is basically conversion? Essentially, when it is turned on and turned off, this is basically PWM is being generated. So on off here. Then when it is on, basically the capacitor that is here, this capacitor gets charged. So the capacitor gets charged, and then when it is turned off, the capacitor basically gets discharged. Again, it gets charged and discharged during the after the capacitor discharges, and that's how there is a DC. Basically, roughly a DC is basically obtained on the load side. Here, if you look at it, basically This is a high voltage unregulated DC. Basically, the voltage may be in terms of 200 volts or something. If you look at it, there is no transformer on the input side. Means it's not basically reducing. What do you mean? What do we mean is there is no transformer that reduces from primary voltage to secondary voltage. The high voltage itself is basically coming here, whatever the 230 volts or whatever. So this PWM, this is basically charged for a short period of time, and for a long period of time it is off. So it is quickly charged, and then when it is off, it is basically gets discharged into the load at the rate the load basically takes current. This charges first, and then basically discharges slow. Charges first, discharges slow. That's how this basically conversion is happening. So the same voltage, this voltage level that it will basically charges to is depends on the on time. Depending on the on time, it will charge to the whatever the required voltage. So the voltage is basically maintained by keeping the on time low to the required voltage. So here there is basically in this, basically there is no drop, voltage drops and stuff like that are not there. Basically it is basically whatever the voltage is there, it is basically transferred. That same energy is transferred to this capacitor to a lower voltage, because it charges linearly, and it will be maintained only to the voltage that is required by this duty cycles. So there is no drop or dissipation into any circuit here, any circuit element. It is simply transferred by conversion process. It works. So this is the block diagram of SMPS power supply, mostly like a flyback kind of power supply that has basically the rectifier, the filter, high speed switching, and basically a transformer for isolation purposes. And then there may be a rectifier or may not be a rectifier here actually, and the filter basically output, and feedback basically from the output back into the control circuit. And here is the control circuit that is controlling the switching here. So it takes the error between this voltage and this voltage, and based on the error, the control circuit would adjust the duty cycle that would basically adjust the output voltage properly. So the output voltage is basically regulated. In DC-DC conversion, these are the different topologies that are basically available. We'll not read all of them. We'll basically just read we'll study the flyback isolated conversion. Typically, there is flyback, push-pull, half bridge, full bridge, right? Similarly, in non-isolated buck boost, hook kind of topologies. We look at buck and boost topologies in non-isolated, and flyback in isolated topologies. So these are the things that we review. Here is a buck converter. So the buck converter essentially typically basically is this way. In the sense the unregulated DC is given here, and the switching, the transformer, the transistor is here. This is basically switched, and there is an inductor and a capacitor here. There is no isolation transformer as you see here. Basically, there is no isolation transformer. What basically, and here is a diode. So let's see how this really circuit works. Basically, in the off condition, the capacitor already has a charge and the inductor already has a charge. That charge basically gets dissipated into the load this way through the diode. The diode conducts, and this is how in the off condition. This side there is no current because this transistor is in off condition. That means the pulse is low here. The transistor is off condition. This is how it is. In the on condition, of course, the pulse is on and the transistor is on. So unregulated DC basically comes here. This would be at a higher voltage than this one. So this diode doesn't conduct, and the inductor basically gets charged and the capacitor gets charged. These two elements keep getting charged. When the inductor charges, the magnetic field basically it is an expanding magnetic field. The magnetic field builds up, and when the
basically again when it goes into the low condition, the magnetic field collapses, or the charge basically is generated, and then the charge is basically delivered to the load. This is how in on condition this basically conducts directly, the transistor conducts and these two charge. In the off condition they are basically this way, the capacitor and inductor produce the charge for the load, and this is how it. So this is how the buck converter basically works. And in buck converter, basically the V output is basically duty cycle into V input. Whatever is the input value, and that times the duty cycle is the V output. That's how the buck converter is. In the boost topology, basically the inductor is on this side, capacitor is again on this side. During the on condition, on condition, the FET is basically turned on. So that means the voltage here is pretty much zero voltage. So it does not conduct here. And so the inductor basically charges here. Inductor charges, and whatever the capacitor value that is there, that goes to the charge is there, that goes to the load. This is in the on condition. So the inductor charges here, but the inductor charge voltage does not go into this one. Here it is transistor is basically in the on condition. This works like a short almost basically, and the diode drop basically is 0.6 volts. This also would be roughly 0.6 volts. So it will not basically conduct in this direction. The capacitor, uh, whatever the voltage that is there in the capacitor, that basically keeps this voltage at a high point, and the charge basically dissipates into the load in the on condition. In the off condition, basically the transistor is off, and the unregulated DC basically gets connected through the charging through the capacitor, and the capacitor charges, and the load also receives current through this circuit. This is how it is. So here in this case, the V out is V in by 1 minus D. V in divided by 1 minus D. There it is V in by D. Here it is V in by 1 minus D is what it is based on the duty cycle. So here the off condition is basically is more prominent. Basically in the off condition it receives current here. That's how basically the V out is depending on the off condition, the 1 minus D. So that's basically boost conversion topology. In boost conversion, this is how typically the topology is based on. We look at now flyback topology. Flyback topology is basically a isolated topology. That means there is a transformer, and typically this transformer is in this circuit is called flyback transformer, because at the fast switching that the transistor happens, what happens to this transformer is basically this coil gets turned on while this is off, and then by the time this coil gets turned off, this basically automatically switched off. So this goes on, and this is off. This after some time this gets turned off, and this basically turns on. So in for the switching, what happens is the flyback transformer basically the coils basically turns on and off alternatively. This turns on and this turns off. Then this turns off and this turns on. Then this turns on and this turns off. Then this turns off and this turns on. That's how basically it keeps on going between these two. That's how a flyback transformer works. That's why it's called flyback transformer. And in the on condition, basically when the transistor is on, in that condition, the transformer basically conducts here, the primary coil conducts, and it goes through this way. So this basically gets charged, and on this side, the capacitor, whatever the charge is there on the capacitor, that basically gets dissipated into the load. This is in the on condition, and this coil is off, so it doesn't generate any voltage, and this path is not conducting, and this is basically simply this way. This is at a higher voltage, positive voltage, and this would be compared to at lower voltage. Now in the off condition, what happens? This is charged. that basically gets dissipated into this. So this is the one that conducts. This basically turns on, and the conducting voltage basically this is at a higher voltage, and the voltage basically goes through this and charges the capacitor and also dissipates into the load. This is how in the off condition it basically conducts. So this is how a flyback off condition is. So, and that's how SMPS power supply works. Let's look at a full circuit of it. Here is the as a flyback SMPS circuit. Here is the full circuit. And if you look at this circuit, is basically the transformer is slightly different. There is not just two coils, but there seem to be additional coil. This is an auxiliary coil. We said there is basically an IC that will be conducting the that is basically controlling the switch that basically turns on and turns off. That switch is basically included into the IC itself. The controlling IC controller and the switch both are basically together in one single IC. This is the drain. So the drain of the switch is basically coming out here. So that way this basically switches through this one here, through this one and to the ground. This is how basically the current basically flows through this one and through the drain and to the ground. So the auxiliary coil is basically here present to power up this IC. We are creating a power supply, we are generating a output power supply, but at the same time the IC also needs power. That is basically more like this power only, DC power, not the unregulated DC. So what for that reason there is an auxiliary coil that generates a VCC, roughly a VCC, and that is the output. This is the output VCC output that's connected through a diode here to a VCC. So this IC basically gets power supply output from the regulated from the auxiliary coil of that, and this auxiliary coil generates the VCC, and so that this IC can actually perform the switching, the fast switching internally. It will have an oscillator inside, and that oscillator basically switches the drain on and off. It has two other outputs. There is a limit inputs. This is a limit input, and then a feedback input, and then a compensating input. These inputs are basically used in regulating the voltages, duty cycle, the current, and all that. So this limit is basically for the adjusting the current. Basically, the ratio here basically adjusts the how much current this can deliver. This will deliver. We'll look at the data sheet shortly, and then read about those things there. And the compensation pin is basically receives the feedback from this output from here. The output is basically fed back through the resistor divider, and through the this side of it is basically connected through the resistor divider and this resistor, and through optocoupler internal. And this optocoupler output is basically connected to the compensator. What happens basically, yeah, let's discuss that. Basically, if the voltage here is going high from the regular voltage, let's say this is designed for 9 volts, and at the 9 volts, if it's not staying at the 9 volts and for some reason it's going up high, then what happens is the current that goes through this one basically increases. The current through this resistor increases because this voltage goes high. This current through this resistor increases. This optocoupler output basically goes down. That means the optocoupler gets turned on. This transistor turned on even more because of this this current, excessive current that is going in. And when the transistor is turned on, its output basically it's more biased. Basically, the transistor is more biased, the output goes down, right? Typically the transistor, that's how it works. with the bias, the output goes 1. It works like an inverter, right? So this basically drops, this voltage drops, the compensating voltage drops, the duty cycle reduces. The duty cycle reduces, then this current will be forced to go down. This voltage will be forced to go down. Whatever was trying to increase beyond 9 volts will come down back to 9 volts. That's how it happens. Let's say this voltage for whatever region comes below 9 volts, then this voltage, this current basically reduces. Because this current reduces, this voltage increases. That means the compensation increases. So the duty cycle increases. Because the duty cycle increases, the voltage here will increase. So that way, this is in a tight loop. If you, for whatever reason, if it happens to be increasing, the loop automatically will basically try to reduce it. And if it is whatever region it is being reduced, the loop will basically try to increase it. That's how this voltage is regulated to whatever the required voltage, 9 volts. The voltage is basically typically obtained by the ratio of this resistor. R6 R7 ratio will determine this voltage, and R2 R3 ratio will determine the current that can flow into this. So it has a built-in 700 volts MOSFET with RDS on of 34 ohms and 11.4 ohms, depending on NCP 1060. There are two part numbers here, NCP 1060 and 1063. The part number for both of them. And the part switches at 60 kilohertz or 100 kilohertz. So one is 60 kilohertz, the other is 100 kilohertz. So it really operates at that frequency, 60 kilohertz frequency. So this is the frequency. It is a 10 pin IC. Of course, one of them is, it also comes in a PDIP7 to 8-pin package. I think 8-pin and 7-pin package. It also comes as an SOIC as a 16-pin package. SOIC 10 comes as a 10-pin package also. So here are the pin outputs. In a 16-pin package, basically multiple drains are there. These are no connect. But basically, those are the only pins: drain pin, limb pin, compensation pin, ground pin, VCC pin, and the feedback. Here is the ground pin that is connected. VCC comes from the auxiliary coil. Limit pin, as we said, the current drawn from the pin decreases. The current drawn from the pin decreases I peak of the primary winding. If resistive divider from the auxiliary winding is connected to this pin, it sets the opposite compensation level, diminishes the peak current. Compensation, the error amplifier output is available on this pin. The network connected between this pin and the ground adjusts the regulation loop bandwidth. Also, by connecting an optocoupler to this pin, the P current set point is adjusted according to the output power demand. So the peak set point, the voltage basically set point, is adjusted according to the output power point. So that's the main purpose of it. Drain is drain connection, MOSFET drain. Feedback is basically, this is inverting input of the transconductance error amplifier. It is normally connected to the switching power supply output through a resistor divider. Here are different topologies, basically, buck converter topology, where there is no isolation. It is basically buck converter, if you remember, inductor and capacitor basically connected, directly, basically on this side of it, and the other side is basically the drain. Drain is connected here on this side, and so this is how, and then the VCC and all that. This is buck converter. Here is the buck boost conversion IC. We are interested in the flyback here. This is the flyback topology, where there is transformer, auxiliary transformer that is powering the VCC, and the drain is basically conducting here. And basically, these are the R6 and R7 ratio. Basically, this is the output voltage. If you want 9 volts here, this IC2, that is basically, it is a reference voltage IC. this reference voltage IC, let's say it is a 3 volts reference voltage IC. And if it is 3 volts IC and you use here basically 1K and here basically a 2K, this is 1K 3 volts and 2K this is 6 volts, so it will be 9 volts. 2K and 1K, that ratio, both of them together basically comes to 9 volts. That's how you basically use this ratio and obtain this voltage based on the reference voltage. This is always trying to put this voltage to reference voltage, whatever the reference voltage is. So R6 by R7 ratio is used that way. Yeah, this is optocoupler that we discussed about. And this R2 by R3 ratio, we look at it. Peak drain current is basically 300 milliamps or 800 milliamps. For NCP 1060, it is 300 milliamps. For NCP 1063, 850 milliamps. That is the peak current. So you can basically adjust the output peak current to some ratio of this. 850 is there. You can basically adjust it to 400 milliamps or a 500 milliamps. Basically, you can generate a 500 milliamps power supply. You can create a 500 milliamp power supply by using a proper resistor there. So if it is 850, that ratio of R1 by R3, R2 by R3, this need to be a ratio of 500 by 850. So 500 by 850 ratio, you need to get it. If you get it 500 by 850 ratio, then you get the output current as 500 milliamps. So that's how it is. Typically, whatever your output current is, you will keep it slightly more than that, so that it will work for more current also. So this is the one that will determine the that current is the one. Basically, what happens is, this is how basically it charges. This is how it charges. This ratio, the ramp is basically steep. This current is basically what is the the peak current that we are discussing right now. So if it is the ratio is high, this will be steeper. If the ratio is low, this will be less steeper. It will be inclined, slightly inclined. So by that it will charge to charge fastly to that voltage and then maintain a higher current basically. So this also basically will be uh, you know will be steep enough so that the more current is basically delivered to the output. So that is basically what determines the ratio determines that linearity here, and the current output current that is basically get delivered out. With the temperature, of course, the characteristics changes. So he has given the temperature, and of course, in this there is no dissipation, so it doesn't really get heated up that fast. So the temperature will be within the normal operating range. The current that basically it can generate is basically is shown 0.93. At 60 kilohertz the temperature is shown, and at 120 degrees the temperature falls drastically to falls to, not drastically, but falls to 0.989 voltage. So this is with the temperature. Of course, this doesn't gets heated up. So if there is some other element that is getting heated nearby, then that can affect this. Otherwise, you don't really have to worry about the temperature curves. Basically, they're all with the temperature it increases. Of course, if you are using in an outside environment artwork, then you have to look at those aspects of it. The junction temperature basically is they're pretty much flat. Basically, the junction temperature doesn't, with the IDSP they don't increase. So that's basically what it is. The optocoupler, we look at it. We used an optocoupler. This here is an optocoupler basically. TLP 127 is an optocoupler. IS127 is an optically coupled isolator. Consists of infrared light emitting diode. Internally, it has a light emitting diode and a high voltage NPN silicon photo Darlington, which has a internal base emitter resistor to optimize switching speed and elevated temperature characteristics in a space efficient dual inline package. Okay, so this side basically one one side is basically a photodiode Here is the photodiode. Basically, as the current basically flows through it, it generates light, and that light basically forms all this photo transistor. And the transistor basically, uh, this is an LED, not a photodiode, LED, and this is a transistor. And the photo transistor basically conducts and basically generates voltage across these two pins. The current transfer ratio is 1000%, whatever current that basically the current that goes here basically get magnified at 1000%, 100 times. It's well. The current, of course, itself draws is very less here. This is an auto isolator that one can use in the circuit. So today we are going to discuss about Bluetooth module, how to interface Bluetooth module. It is a pretty straightforward method. Basically, Bluetooth is wireless connectivity in short range, about 10 meters typically. Frequency range is basically 2.4 gigahertz range, 2.40 to 2.483. That's the frequency range it operates in. And there are many variants of Bluetooth, 3.0, 4.0, 5.0, and BLE. I think the 5.0 boasts about 100 meters are close to that kind of range, and it coexists with Wi-Fi networks. The Wi-Fi networks can be there, and Bluetooth can coexist along with the Wi-Fi networks. A Bluetooth module is basically typically a dedicated microcontroller based module. It manages Bluetooth stack. The Bluetooth stack is basically manages transmission and reception, manages the power, error correction, many software activities like managing the channels, spread spectrum, managing discovery, registration, addressing, and all these activities. The Bluetooth stack does it. So to run a Bluetooth stack, a microcontroller is needed because of this software functionality that is implemented. A microcontroller is need to be present. So design typically uses a dedicated microcontroller for Bluetooth for modularity and stack reliability. So you don't have to port the Bluetooth stack onto the application microcontroller. So the microcontroller that's basically runs the Bluetooth is separately put into a module, Bluetooth module. What is a Bluetooth module? It is basically a small PCB. It includes antenna and RF baseband and all that. Includes Bluetooth stack and a simple hardware interface. It offers a simple hardware interface, either UART, I2C, or SPI interface to the main microcontroller. So the main microcontroller application control is residing on the main board, and then that basically communicates to the Bluetooth module through UART interface, basically. Simple software interface, either raw packets are basically sent or AT commands. It uses AT commands. AT commands is basically a software interface for communicating with telecom modules, basically. This is more of a hobby interface module that basically has TXD, RXD, ground VCC enable. A UART interface is given here, and enable pin. This is how basically Bluetooth module. So the way you interface is basically this is your microcontroller. The microcontroller RXD and TXD of the UART, basically RXD and TXD are connected to the RXD and TXD of the Bluetooth module. Ground is connected to ground, VCC is connected to VCC. And if there is an enable pin is usually connected to the 5 volts, basically, or the VCC, whatever, if it's 0.2 volts. The module, basically, Bluetooth modules really come this way, like stamp module. The PCB is basically the hole is half cut holes basically across the PCB edge, basically. They are soldered onto pads basically on the PCB. This is the PCB. The PCB has pads basically. Provision of pads is made here, and Bluetooth module PCB basically soldered onto the main PCB this way.
it's soldered onto the main PC. This is the way the Bluetooth module basically gets attached. The main controller communicates with the UART basically using RxD and TXD. So that's basically what we're saying. Bluetooth stamp is there, and then microcontroller there, and RX and TX through them it would communicate. The rest of the application board can have an LCD or a flash or SRAM, the sensors and all that are there, and it communicates, enables basically the Bluetooth stamp enables the device to basically wirelessly communicate with the other devices and all that. So it wireless enables the your application, whatever the application. Here are some Bluetooth module examples. HC05, Arduino open source module. Uden, I found it interesting, so I put this. It's basically very small modules compared to other them. This is a very small, 3.25 by 8.5 by 0.9. Typically ideal for smartwatches and those kind of solutions. Okay, this is a microchip Bluetooth module. This is how it is, and the antenna is here. Basically, it's a trace antenna on this one itself, and here is the module. Basically, the this can be connected to the MCU using RX and TX. Basically, of course, it also seems to have RTS and CTS input, so RTS CTS can be used. It has a reset button that can be connected to GPIO. Other PIOs. These GPIOs may or may not. They're really not required. The required are basically RX and TX are definitely mandatory for communication purposes. RTS, CTS are not necessary, but if you connect, basically the Bluetooth module will have flow control option. Basically, this is how the module is. Basically, these are the so many pins that are there: UART, RTS, CTS, TX, and the GPIOs basically. And another pin, important pin, is reset pin. This can be connected to VCC, basically reset pin, or this can also be connected to GPIO pin of microcontroller. So microcontroller can reset whenever it likes it. There seem to be SPI also on this, but let's see if the SPI is really. SPI interface is primarily used for factory programming, test, and diagnostic. Although not required, the SPI interface is useful restoring a corrupt flash image. Okay, this is basically for the flash image and all that flashing. So this you don't normally use it. We don't have to use it. So we can just use the UART basically and interface Bluetooth module. So Bluetooth modules is basically that simple. Here is basically a smartwatch schematics that we have seen earlier. Here is the one. If you see, here is a Bluetooth module. Simply we are using it's much simpler module with much fewer connections than what normally other Bluetooth modules are. So it's only 16 pins that the module has, and your RX and TX. So you bring the UART RX and TX and connect it to the microcontroller. Here is the microcontroller, UART RX and TX. They are connected here. So that's how you connect the Bluetooth module. Then the software in the microcontroller can communicate with the software in the Bluetooth module. This Bluetooth module. So that's straight forward connection. So there is not really a great deal of. And then VBAT is connected to the VCC. The GPIO pins are not used basically. You can use the GPIO pins, then through the UART interface you can control. Typically it will have an API or something through which basically you can configure the GPIO pins, set values on the GPIOs and all. That's the GPIO that we are basically talking about in the block diagram in the PowerPoint presentation. These pins, GPIO pins. Typically, all Bluetooth modules will have
spare GPIO pins that can be used for that purpose. So this is how the GPIO Bluetooth modules. There is probably one more VT840F, another Bluetooth module that this is from the Panstem module. I think this is the module that uh, the schematics is using. This is Panstem VT840. The it is using 4871. It's RN4871. It's another module, not that module. So the right here are the Panstem modules. Basically, they include basically ARM Cortex M4 processor within this module. Basically, underneath this metal shield, you'll have the microcontroller and all that. So that microcontroller runs the Bluetooth stack and all that. So it's a dedicated microcontroller for Bluetooth stack. And the GPIO's UART, there it is, UART interface is there. There may be other, because that's a microcontroller, there is usually many other peripherals to it that the module vendors bring it out to the external. Basically, they'll bring out all those pins to it, but you don't want to use all those pins because some of those pins may be internally used and all that. So only for the mechanical ruggedization, basically you can solder them so that solder them to pins that go nowhere, so that it basically rigidly fixed to the module. Other than that, you don't use those pins. There are so many pins that are there. So lot of them are GPIOs. Here is the list of and some analog inputs are there. Preset pin is one thing that you bring out. Then it does seem to have a lot of GPIO pins that we don't. All the ground parts you connect it basically. Ground is you connect it to ground, right? Wherever the ground is there, that ground basically you connect it. So this seem to excessively too many pins on this for the module. But yeah, so one need to be careful and connect all the ground pins though. If you don't connect all the ground pins, it may not function properly or may give some intermittent errors and all that. So that is the thing that one need to look at. Here is the module, Panstem module, soldered onto a main board basically. Here is how it is soldered onto. So yeah, that's that. Now we'll look at there is still time. I'll look at we'll look at Zigbee also basically. Now looking at Zigbee modules, the interfacing is similar to Zigbee module also, but Zigbee module will basically what is Zigbee will look at. Zigbee is also a wireless connectivity. It's short range, typically 10 meters to 100 meters range, and it is guided by IEEE standards. 802.15.4 is the standards that basically specifies Zigbee protocol and Zigbee standard and all. It is an alternative to Wi-Fi and Bluetooth. It basically can run up to a maximum data rate of 250 kbps data rates. So on a UART, you can easily run it at 112 115 kbps to 50 kbps rate. You can set it, and then you can basically run it on the UART. Commonly used in sensor networks. It's commonly used in sensor networks. Operates in ISM bands. 868 megahertz, 950 megahertz, and also 2.4 gigahertz band. That's how Zigbee is operational, and Zigbee also uses encryption. So data encryption, the modules can be module data that is coming from the modules can be encrypted, so that droppers cannot actually read the data and all that. It implements ad hoc wireless mesh networking. All the nodes basically, Zigbee nodes form a mesh networking, which basically ad hocly forms the network, and they basically detect each other nodes and then form the network ad hocly. It can be used in battery operated devices due to its low power. So that's basically typical Zigbee module. Again, the same way. There may be an external antenna. This is a chip antenna that is there, and basically the stamp module where the half cut holes are there. These can be soldered onto the on the pads of the main board, and so it will piggyback onto the main board and basically form. Underneath this, you will see basically the microcontroller, the controller that would basically handle the Zigbee stack. The Zigbee stack, as usual, basically similar to the Bluetooth, manages transmission, reception, power, error correction, channels, spread spectrum, manages all those discovery, registration, addressing. All these things are handled by the Zigbee software. There would be a software on the Zigbee module, and that manages this entire software tasks. And it would be a dedicated module. We don't put application software onto it. It is a dedicated module, and so that module, we are not stack will be reliable, uh, so that we don't have to interface with additional third-party interfaces and all that. That doesn't have to be done. And Zigbee, it will be modularly. It will also add to the module. It will be separate module and running of it. So the Zigbee module is basically a small PCB that we have seen in the earlier slide, and includes antenna, RF baseband, includes the Zigbee stack and all that, and offers a simple hardware interface, either through UART, I2C, or SPI. Usually UART. UART is the most common because it's a simpler interface, and the software can be all either through raw commands or AT commands can be used. Module allows to modify the software need or interface another microcontroller. You can also change the software, download a newer version onto these modules and all. That's the interface. Basically, here we are showing it. This is how we attach the module to the data, the main board, and this is the interface. This is RX and TX microcontroller. Basically, connects to the Zigbee stack. So here are some modules: DZ, NXP, Silicon Labs, Microchip. These are all the modules that are available for Zigbee. Of course, again, once you go to the Mouser, you may see some more companies, some more modules and all. Let's look at basically some Zigbee modules. Here is a Atmel Atmel ATS. Yeah, here is a basically a module, Zigbee module. It has, these are all the pins that are there on it. SO, SOI, SCLOP. So serial flash interconnect. This is obviously with an SPI flash. It has an on-chip flash that can be programmed, but we don't want to tamper with this. This basically we would not connect to the microcontroller, so it's not available for the microcontroller. The UART, RX, and TX, they are basically available for the pin 14 and 15. Can be connected. RTS, CTS is also there. The flow control is also there. So those you basically connect to the main microcontroller. And yeah, so main controller. Then it may have some signals that you basically transform to the. So those are all the pins that are there. Yes. So SPI, we don't use. RXD, TXD is 0. Those are the ones in 22, 23, I think. It also has I2C interface. But yeah, I think the I2C, we need to see if it is available for microcontroller. So this, let's see how much current it would consume basically. IDD, it's consuming about 4 milliamps basically in a normal mode. But if there is a transmission that happens, it would be 10 milliamps. With the transceiver in on state and TX state, transmission state, 10 milliamps is what it will draw. So that's the power it consumes. One needs to budget that kind of power basically for it. Basically, VDD is a 3.2 volts module, so very convenient for CMOS microcontrollers and all that. You basically use 3.2 volts supplying the VDD to the system. So those are the key specifications there. The antenna will come like, okay, additional software details and all that he has given, and there are additional module document reference documents that are here. That is sheet. So this is basically how a Zigbee module. There are more Zigbee modules that we can probably see in another Zigbee module. They all basically essentially have UART. Yeah, this is the this module that. So we look at the pinout. Yeah, here is the pinout. Yeah, of course, this is says not recommended for new designs. So it is there basically, it's no longer recommended for new designs anymore. Just for our learning purposes, we can look at it. So it has all these outputs. There is CTS, RTS, and RXD and TXD. Here is the RXD and TXD 217 and 18. And it has JTAG interface for essentially downloading code, upgrading code, and all that. These modules. So it's basically acquired by Silicon Labs. JTAG is there for downloading and upgrading the firmware on the this module. Of course, you basically use whatever the module as is. You may not upgrade the firmware module. If you basically want to provide the provision of the firmware upgrade, then you have to bring in the JTAG to a connector and all. Again, this JTAG you need to JTDO, JTDA, JTMS. You need to bring that basically. Okay, port and JTCK. These are the things that need to be brought out to port. But typically, module comes with software loaded. You will never generally modify it, and you can tamper with it. Basically, whatever module functions well for you, that is the one that you use. It you no longer modify it. So you don't have to bring out the JTAG output into the output. All you bring out is the UART, RXD, and TXD onto the microcontroller, and of course, RTS, CTS can be brought out also. So if RTS, CTS is available on the microcontroller, you connect RTS, CTS also. That will have flow control options. So flow control can also happen. Let's look at how much power. Yeah, power it is mentioned. This is operating on a 3.2 volts, and supply voltage PCL. The high sleep. In sleep mode, it's 1 microamp. Very little. Yeah, 52 milliamps. So this is a little high power module. It consumes 52 milliamps. Transmit current consumption at 20 dBm output at minimum module output power 52 milliamps. So if you are basically operating it on long range and all that, 140 milliamps is the current that it draws. So you need to prepare for that kind of 140 milliamps is what you need to prepare for basically. So I think if we have specified the range on it, we will see. Yeah, generally I don't think they specified the range. Basically, one you put it into the design in the prototype board. Basically, you test it how much range it is giving and all that. One has to practically try it, then understand the range. Is it coming to 50 meters, 100 meters? What is the range that it can reliably work and all? Only by using one can probably get a kit and then start using it. Basically, that's how it is. So that's the Zigbee module. That's the interface. Zigbee module is operated layered at 7 ISO say layer. It basically operates in physical layer, MAC layer, and network layer, security application layer, and all that. This is how it is. The stack is typically organized, and the MAC layer would have that MAC address, typically 40-bit. This address, 64-bit address. The MAC address would be a 64-bit address. Out of that, 40 bits are basically assigned by the manufacturer, and 24-bit is unique to the organization unique ID, OUI. Organization unique ID will be given, and remaining will be this 40 bits, basically these five right here are basically assigned by the manufacturer, so that you can use this unique MAC address. MAC address and it will be unique for configuration purposes and all. Network layer is basically it can operate like a star network, mesh network, tree network. These are the way it can operate. And any Zigbee node basically typically it should be configured as a coordinator or a router and an end device. There are three different modes that it would have. One is a coordinator, and the other is a router, and the other is end devices. There would be only one coordinator in the entire Zigbee network. Routers, there will be multiple. So typically, if you look at it, this is a star network, tree network, mesh network. This is basically a mesh. Basically, they're all connected in different, mesh fashion and all that. So there would be only one coordinator in the entire network. That coordinator is basically keeps track of what services are offered by each one of the end devices, each one of the Zigbee devices. What is services it offers? It registers. Every one of them will register on this. So other nodes can basically avail those services. So it would be basically in registry maintenance is what is done by the coordinator. Router is again a special node that can actually route packets. Basically, it can receive a packet from here and send it to another node. So the routers are also basically important. They play the role. The end device is basically just it's a functional device. It only operates whatever its function is. If it is a sensor node or something, it will be a sensor node. What kind of sensor node it is, it will post to the coordinator, and all other nodes can avail the temperature sensor. Let's say can avail the temperature from this node, etc. So this is how it is. So end devices are basically depend on the routers for communicating with other nodes and all that. And they all depend on the coordinator for discovery of what services are available from the devices and all that. And there are many application profiles that the Zigbee implements. They're like home automation, commercial building automation, smart energy, personal home and hospital care. For all these, APIs are standardized. The APIs, the application profiles, basically includes a set of API that nodes can call and all that. The specific APIs and messages are defined for each application profile by Zigbee Alliance. Zigbee Alliance is the one standard body that creates the standards. So that's how the Zigbee nodes basically communicate and all. So Bluetooth and Zigbee pretty much similar, including those modules into the design. You have the entire design and you have the module on, piggybacked onto the main board and connect it through your interface and communicate that. You don't need any level converter and all that. Typically, it works at the 3.2 volts UART. You would basically need to ensure that the module operates in whatever the microcontroller is operating. The microcontroller is operating in a TTL 3.2 volts. You have to look at that the module also is operating. You choose a module that can also operate on 5 volts range, or both operating on the 3.2 volts. lot of the modules basically these days, because of the most of them are 28 nanometers semiconductors and all that, so operate at 3.2 volts ideally. So so they're all interoperable, easily can be interfaced with each other. So with that, we are done with the Zigbee module.